Welcome to CSAI Think, Tinker, Learn. Today, we are kicking off an exciting new series on system design, where we pull back the curtain on how the internet actually functions. We're going to look past the buzzwords and dive straight into the engine room, the TCP/IP stack. This series is designed for engineers who want to understand the machine, not just memorize a textbook. To help you along the journey, we have launched a companion site. Uh, it's a GitHub pages. The link will be in the description. And today we are going to cover the topic OSI model and TCP/IP fundamentals. On this site, you'll find in-depth articles that pair perfectly with these deep dive videos, giving you a resource to reference long after you have watched the videos. If you enjoy this kind of technical deep dive, please hit that like button, share this with a colleague who needs to brush up on their networking, and make sure you subscribe so you don't miss the rest of the series. Let's get on to it. Before the internet became the streamlined machine we use today, we lived in a world of vendor lock-in. Back in the pre-1984 era, networking was a mess. Hardware and application logic were inextricably tangled. If you changed a network card, your software broke. Enter the OSI model. Its genius wasn't just in defining layers, it was in the clean abstraction. By enforcing a separation of concerns, the OSI model ensured that each layer only talked to its direct neighbor. It separates how to move data from how to present data. Remember this core principle. In software design, never mix your physical transport logic with your application state. Keep it clean. When data travels down the stack, it undergoes a process called encapsulation. Imagine taking a letter, putting it in an envelope, putting that envelope in a box, and then creating that box. At each layer, we wrap the data in a header. We start with the message at layer 5 through layer 7. As it hits layer 4, we wrap it in a TCP header, turning it into a segment. At layer 3, we add an IP header, making it a packet. Finally, at layer 2, we add an Ethernet header and a checksum, creating a frame. Crucially, each layer operates independently. Layer 2 doesn't care what's inside the IP packet, it only reads the Ethernet header. And a word of warning, watch your MTU, maximum transmission unit. If your packet is too big, it will shatter into fragments, which is a performance killer. Avoid fragmentation at all costs. Let's zoom into the physical foundation, layer 1 and 2. Layer 1 is the raw reality. It's just bits traveling via voltage, light, or radio. Layer 2 takes those raw bits and builds structure, creating frames. The algorithmic magic here is the CRC checksum. When a frame arrives, the receiver recalculates the checksum. If it doesn't match, the frame is silently dropped. It's an efficient fail-fast mechanism. Also, note the 48-bit MAC addresses. They handle hardware-level access on the local network. Pro tip from the trenches. Always check layer 1 first. I've spent debugging complex, impossible software bugs, only to find the culprit was a poorly cramped Ethernet cable. Start at the physical layer every single time. Now we move up the global router layer 3. MAC addresses are great for a local home network, but they aren't enough to navigate the entire planet. Layer 3 introduces hierarchical IP addresses to route out data globally. How does it do this? It relies on path selection algorithms and address resolution protocol, ARP for short, which maps logical IP addresses to hardware-specific MAC addresses at every hop. But things can go wrong. Routing loops occur. That's why we have a time to live counter. Every time a packet hits a router, the TTL decrements. If it hits zero, the packet dies. It's a vital safety wall that keeps the network from choking on infinite loops. Welcome to the L3 deep dive now. We actually ran out of IPv4 addresses years ago, which is why we use CIDR notation to mathematically divide an IP into a network prefix and a host identifier. But the real hero keeping IPv4 alive is the network address translation or NAT. Think of NAT as duct tape for the internet. It maps internal private IPs and ports to a single IP. The router rewrites header on the fly. It's brilliant, but it comes with a cost. It breaks stateful peer-to-peer connection. As an engineer, you need to understand this, especially when you are trying to punch holes through firewalls for your applications. If layer 3 gets a packet to the right building, which is the IP address, how does it know which room to go to? That's where layer 4, our traffic cop, comes in. It introduces 16-bit port numbers, ranging from 0 to 65535 to multiplex traffic. Think of the OS as the receptionist in this building. When a packet arrives, the OS reads the destination port in the transport header and delivers it to the correct application apartment. Ever seen an address ready in use error? That's your OS telling you a zombie process is already hogging that port. Go find it and kill it. TCP is famous for illusion of reliability. The internet is inherently chaotic, dropping and reordering packets constantly. But TCP gives us a nice orderly byte stream. How? The three-way handshake. SYN, SYNAC, ACK. It ensures both sides are ready to talk. Crucially, every byte is numbered, and the initial sequence numbers are randomized for security. If they are predictable, attackers could inject malicious data into your stream. If an acknowledgement doesn't come back within a timeout window, TCP simply retransmits the data. It's persistent, and it's why your web traffic actually arrives intact. TCP isn't just reliable, it's inherently polite. It manages this through flow control and congestion control. Flow control stops a fast server from overwhelming a slow mobile device, while congestion control stops the whole network from collapsing under too much traffic. The algorithmic engine here is AIMD, additive increase, multiplicative decrease. TCP probes the network, speeding up until it senses packet loss. Then it immediately breaks and scales back. This creates that characteristic sawtooth graph. The algorithm is literally why the internet doesn't collapse under its own weight every single day. So when do you use TCP and when do you use UDP? This matrix is a cheat sheet. TCP is connection oriented, reliable, and ordered, perfect for HTTP databases and SSH. But UDP, it's fire and forget. It's connectionless, fast, and best effort. Don't use TCP for real-time multiplayer gaming or live video. Why? Because TCP is too polite. If one packet drops, it pauses the entire stream to wait for a retransmission, leading to a head of line blocking. In live video, you'd rather drop a frame than suffer the entire stream. Now we have reached the top, the user space, layer 5 through 7. While the textbooks list these as distinct modern implementation, usually merge them. This is where your JSON lives, where TLS handles your encryption, and where your HTTP application logic resides. As a developer, you live here, but never forget everything you build rests on the structural integrity of the six layers beneath you. Your application has no idea if packets were dropped or reordered down there. It just expects the transport layer to hand it a clean, reconstructed byte stream. Let's look at the practical subsystem, DNS. It's the Internet phone book, and resolving a name is actually an iterative graph search. To minimize latency, we use aggressive caching at every node. Under the hood, DNS almost exclusively uses UDP. Building a full TCP three-way handshake just to ask for an IP address would be too slow. And a word for advice, whenever you have a weird network issue, check DNS first. Expired TTLs, tail caches, or cache poisoning are common culprits. Until proven otherwise, always assume DNS is broken. So, why the discrepancy between the 7-layer OSI model and the 4-layer TCP/IP model? OSI is a theoretical reference, born in 1984. TCP/IP is a practical implementation from the 1970s. The internet chose the practical route. TCP/IP collapsed the top and bottom layers because, in practice, dividing session management from application logic was just unnecessary overhead. The lesson here? Learn OSI to pass the interview, but learn TCP/IP to do the job. Let's put the full system in motion. What happens when you type google.com into your browser? A single key press triggers a massive lightning fast cascade through all 7 layers. You've got a browser caching, UDP DNS resolution, a TLS handshake, the TCP three-way handshake, an HTTP GET request, and finally L3 IP router. This is the ultimate system design question. Being able to walk down the stack like this proves you just don't know the definition. You understand how the pieces of the machine actually interlock. Finally, for the big engineers in the room, here is the engineering debugging matrix. When things break, don't guess. Walk the stack from the bottom up. If curl says 404 not found, you're dealing with an L7 or layer 7 application logic. If your SSL checker reports a certificate error, look at level 6 or layer 6. Connection refused usually means the process isn't listening on port level layer 4. If you can't reach the server at all, you're likely looking at a physical routing or firewall issues in L1 through L3. To wrap up, I'd love to hear from you. Which of these layers do you find yourself debugging the most in your daily work? Does DNS haunt your dreams? Or is it the mysterious layer 4 port issues? Let me know in the comments below. If there is a specific topic or a deeper layer you want us to dissect in a future video, leave a request in the comment. We read them all. Don't forget to like, subscribe, and share this with your team. Thanks for watching and keep tinkering.